Okay, thank you for the introduction. Today I'm talking about my work with Sriram Khanna, Seung-Oh, and Pramod Viswanath. This work has been published in NIPS last year, and it was a spotlight presentation. So the problem setting is very simple. Assume we have some ID samples, x, y, y, from some joint distribution. We want to estimate the mutual information between the pair of random variables. So this problem is very easy, and it has a lot of applications in different areas. For example, in computational biology, there's a common task called gene network inference. You have a lot of data of the gene expressions and the protein expressions and something. Biologists think that the genes and the proteins interacting with each other through a network. Our goal is help the biologists to detect or to kind of test the network from data. There's also a recent interesting work which uses information bottleneck to explain deep neural nets. So they try to quantify the mutual information between the inputs, outputs, and the internal neurons of the neural nets. So we need to estimate the mutual information between input, output, and neurons to get some sense. So there are a lot of applications like that. But a baseline algorithm is estimating mutual information. So it seems a very classic problem. So actually, there are a lot of very classic algorithms for doing that. But when we do the mutual information estimation for some biology problem, we found that sometimes we get a negative answer between the pairs of genes. Well, if you know some information theory, you know mutual information is always non-negative, no matter how. So what's the problem? So some may say because you don't have enough data points, so it should come from some estimation error. But the case is that even with many data points, the answer is not converging to some positive quantity. It's converging to some negative quantity. So why is that? This is kind of mysterious. So, but if we plot the histogram of the gene, so we know the answer because the histogram is kind of look like the figure in the left. So some of the gene, the expression is 0, some is 1 because of quantization or something else. Well, the other is has some distribution between 0 and 1. So this suggests us to study the mutual information between a mixed distribution. Well, there's another another example is when you measure the mutual information between neurons of neural network. Suppose you're using ReLU, which is a very popular activation function. The output of ReLU is actually a mixed distribution because it has some probability to be 0 and some probability to have this continuous distribution of positive numbers. So that motivates our work to estimate mutual information for a mixture of distribution. So this is the most general definition of mutual information based on probability measure. Maybe it's too long for everyone to read, but I want to emphasize that it only requires that Pxy is a probability measure. It doesn't need to be continuous to have a density function, or it doesn't need to be discrete to have some probability mass function. So our goal is to design an estimator for mutual information for that general case. In general case, we say we want to cover the following cases. The first is X is a discrete distribution and Y is continuous. Or XY can be high-dimensional random variable where some dimensions are continuous and some are discrete. Or XY is like what I said before, it's a mixture of continuous parts and discrete parts of distribution, or any mixture of both cases. So this is, I think, very general that can cover most of the real-world applications. So the outline of the talk is we first introduced the new estimator of the mixture of random variable, and we proved the error-to consistency of the random variable and show some simulation and real data performance. Sorry. First, if you don't know how to estimate mutual information in the mixture case, you will think we will reduce the problem into either discrete or continuous. So the first method is we can quantify the data to make it purely discrete. But this is first sensitive to how to quantize the space. Also, if you are doing a really high dimensional case, quantization, the number of quantization is exponentially large to dimension. So this method is not so good for high dimension. The other method is you can reduce it to purely continuous. But how to do that? So maybe one naive is you add a very small noise, small perturbation to every single noise. But that's very sensitive to the noise. So there are no, as far as we know, there's no consistent estimator for mutual information in mixed case. So what we do is we start from the very classical mutual information estimator for continuous case, which is called KSG estimator. This is estimator based on K nearest neighbor method. So we pick a hyperparameter K, and for each node, we find the K nearest neighbor distance, the distance of K nearest neighbor to call it rho y, rho xy. The next step, we keep rho x, the x distance, same as rho xy, and we count how many samples whose x distance is smaller than this quantity. We call it kx. Here, kx is the number of samples between these two lines. Similarly, we get ky. So the KSG estimator is 1 over n, the summation of phi k plus log n minus log kx minus log ky, where phi is diagonal function. But here you can just think phi equals to log. The intuition is that if near this point, pxy is approximately equal to pxpy, then k over n is approximately equal to pxy, and the kx over n is approximately equal to px, and ky over n is equal to py. So that's the intuition behind the KSG mutual information estimator. So one advantage of KSG is that by doing this kind of cancellation in the formula, we don't have rho xy here. So this is very crucial when we go to the next step, when we go to the mixed setting. So let's go to the mixed setting. So we propose the following estimator by just changing one parameter in the KSG estimator. We change k to k tilde I. So what is k tilde? If I is a continuous point, we just let k tilde I equals to k. If I is a discrete point, so we count the number of points, number of times that the particular point was seen. It's kind of the number of multiple points at this at this sample. So we can say that in purely continuous and purely discrete, there's two extreme cases. Our proposed estimator covers the previous estimator. For if the distribution was purely continuous, it's very easy because k tilde I, as we said, is always equal to k. So it's identical to KSG estimator. So if the distribution is purely discrete, then let's say kxi is just the number of samples on x, kyi is the number of samples on y, and k tilde is the number of samples on xy. So the definition of mutual information gives us mutual information is actually not equal, it's approximately equal to the empirical average of, it should be 1 over n, sorry. Empirical average of the log of nxy over n divided by nx over n times ny over n. So it's simplified to this. And this nx, nx and this nxy over n is approximately equal to pxy, nx over n approximately to px, and ny over n approximately to py. That covers the most simple plug-in estimator of mutual information in discrete case. So by just simply doing replace k by k tilde I, we will extreme classical estimator in these two extremes. And also we could show that for any distribution such that the mutual information is well defined, our estimator has to add true consistency under these assumptions. For these assumptions, I want to point out number one is a case function of n which increase Sn, but not so fast. And these 2, 3, 4 are some technical assumptions, but I was able to show that for all the cases as I showed in the previous slides, they satisfy all these technical assumptions. So let's look at some simulations of our setting. First, we do some synthetic simulation of just estimating neutral information. The left is x is discrete, y is continuous. The right is xy is a mixture of continuous and discrete. Here, the red star is some discrete point, and the blue dots comes from a continuous distribution. We can see that here our result is the black line. The red and pink line are partitioning or quantization-based algorithms. This blue and green line are based on KSG, and the noisy KSG, I mean just add some noise to each sample. We can see that for both of the cases, our estimator is consistent. Our mean square error decrease as the sample size increase. Well, some other will even increase because they don't have consistency. And some other algorithm may be better than our algorithm in some case, but there are no algorithms that can beat our algorithm in every case. So we further apply our algorithm to some tasks. First is a feature selection task. Suppose we have some feature, some random variable x1 to xp, and we have observation y. It's only depend on subset of x, only a small subset. So given observation y, we want to figure out which feature is relevant to y. We make it a little bit harder because here we call observation a zero inflated version, which means y has some probability to be zero, to be eliminated. We don't know why. Our algorithm is very easy. We apply our mutual information estimator to every xi and y. And if the mutual information between xi and y is greater than some threshold, we will select it. So we are able to plot RC curve for this task, and we can see that our proposed algorithm is the best. It's to the up left corner, and there are some other algorithms. Also, we use our method to the gene network inference, which appears in the first slide of my talk. So we have 20 genes connecting each other through a network. So in this setting, we assume that the biologists already know the network, but they want to kind of test whether their hypothesis is correct. So we say if the mutual information of two pairs of genes greater than some threshold, we think they are connected. And we are also be able to plot the RC curve. Also, there has some dropout, which is to say gene is missing with some probability. It has some probability from the raw data, but to make it harder, we even put more probability. So we can see that this is area under RC curve, and this is a different level of dropout, different probability of dropout. We can see that our black line is on the top. So as a summary, in this paper, we propose an estimator for the mutual information for continuous discrete mixtures and proved consistency and shows both synthetic and real data performance. So there's still a very big open problem, which is the convergence rate of our estimator. The convergence rate of KSG estimator has been studied somewhere before, but in this case, because the mixture distribution is kind of quite complicated because some dimension or something else. So this convergence rate is still a very open problem. Okay, that's it.
We have time for several questions. Okay, so if there's no questions,
So the feature selection problem, would it be better to do it collecting a bunch of features at a time and then computing mutual information? And can your algorithm handle that? So instead of doing one at a time, you really want to know which subset of features
Yes, you mean you don't do it one by
yeah.
one, you select a subset.
Mm-hmm.
Yeah, it's kind of it's correct, but the problem is you have to select a subset of Q element from P. If this coordinates P and Q are large, they'll be very huge.
Mm-hmm.
So we try to do that, but this is doing one feature at a time is I would say as same as doing two features of that together at a time. But doing Q may be better, but computationally is cost too much.
Okay.
Any other questions? All right, so let's thank the speaker one more time.